Alright, this is it. This is chapter 26, final chapter of the year. This is going to be on electromagnetism, which is the culmination of studying electricity and studying magnetism separately, and how we put them together and how that creates light. So, we learned in the previous couple of chapters that when you have a changing magnetic field, it can produce current in a wire, but you can ask yourself, what's happening in the wire, or what's happening in the physical space around the wire that's causing that current to flow? And would that same effect be happening in that physical space if there wasn't a wire there? Is it something that only happens if there's a wire there, or is it something that's happening in the space regardless of whether the wire's there? And a wire being there allows you to see and measure what's happening, but even if there was no wire, something would still be happening in that physical space. So what is it that's actually causing this current to flow? And so it turns out the physical result can't depend on if you put a wire there or not a wire there. So it has to be something that's happening in physical space itself. And so what causes current to flow or charges to move is an electric field. And so when you have that changing magnetic field, what it's causing is an electrical field in space, and then that electrical field is what's inducing the current to flow. So if we take all wires and physical things out of it, we can still have this kind of idea where if you have a changing magnetic field, it induces or causes an electric field. Okay? And so this electric field now causes current to flow if there's a wire there, but even if it's empty space, there's still an E field. But then, interestingly enough, it turns out, if you have a changing electric field, which you have because this electric field just got turned on by this magnetic field, that a changing E field then causes or induces a changing magnetic field. And so the electric field and the magnetic field, they keep inducing each other back and forth. So once you set it off, once you start it going where say you create an electric field out of nothing, it pops up. The creation of that electric field then was a changing E field, creates a magnetic field, and that new magnetic field creates a new E field, and that creates a new magnetic field, and back and forth essentially forever. So it's a chain reaction of electric and magnetic fields inducing each other back and forth, and they propagate through space, and that's what we call light. So when you see photons or light, you might have heard of it called as the electromagnetic spectrum or an electromagnetic wave. That's exactly what it is. It's electric and magnetic fields that are oscillating and self-propagating each other and traveling through space. And of course they travel at the speed of light because they are light. So when we were studying light, 10 chapters ago, we talked about having a wave-like properties and particle-like properties. These wave-like properties are because it's an electromagnetic wave. It's an electric field and a magnetic field that are oscillating. So it can have different wavelengths, of course. That's related to how fast it's moving and the frequency at which it's oscillating back and forth, which has to do with the source of the wave. So all these electromagnetic waves, regardless of their frequency or wavelength, all travel at the same speed, which is the speed of light. So it was a pretty important discovery that electromagnetic waves travel at the speed of light, because previously they were thought of as two different things, and this allowed scientists to realize that they're actually the same thing. So you have the same spectrum we had before. Visible light is roughly 400 to 700 with a little bit of a fringe on each side. But this picture here is really kind of good to focus on. So the things to notice are that the electric and magnetic fields are perpendicular to each other, and they oscillate like this. So when we were learning about, here, let me see the slide. Yeah, connect back to polarization. So when we were learning about polarization before, we learned that a Polaroid filter only allows one orientation of light through, but you didn't really have a good idea or conception of what we meant by the, quote, orientation of the light. And so now if you understand light as an electromagnetic wave, you can see that the electric field has a certain orientation, like, for example, on the y-axis, and then the magnetic field is perpendicular to that on the x-axis. And so those Polaroid materials, or polarizing materials, they interact with the electric field based on how the electrons are able to oscillate within the crystal. And that can either allow the wave to pass through, or if the electrons can't oscillate and propagate the wave, then it will stop it and not allow it through. So just like we had before, the waves propagate at the speed of light. So this formula is really the velocity equals wavelength times frequency, but the velocity in this case is c, which is the speed of light. And you need to remember that the value of c, if you've forgotten, is 3 times 10 to the 8th meters per second. So you'll need to use that for some formulas in this chapter to calculate frequencies or wavelengths or colors of light or things like that. Okay, so the other thing in this last chapter is using these electric and magnetic fields to find important properties like the charge and the mass of fundamental things like electrons or protons or ions. And the reason is this is really valuable is because you can't exactly take an electron or a single atom of oxygen and put it on a balancing beam and find out how much it weighs. So you have to use kind of more clever or creative techniques to find the charge and the mass of these really, really small scale objects. So we're going to see how we can use electric and magnetic fields to do that. So here's the idea. When you have a charge moving through a magnetic field, if the magnetic field is perpendicular to the direction the charge is moving, then using the right-hand rule, the force will be perpendicular to that. And so if you have a velocity, say, to this side, and a magnetic field into the page, the force is up. And that bends the particle around, and the force is always perpendicular to the velocity, which means it's always going to be pointing towards the center. So this particle will undergo circular motion. So the magnetic force is causing circular motion. So we can set these two forces equal to each other. The actual force is magnetic force, and the effect of that is circular motion. So QVB is the actual force, mv squared over r is the net effect of that. So we set them equal to each other and we solve for mass. So if we know the strength of the magnetic field and the velocity of the particle or the charge of the particle and the radius, we can find the mass of it. So typically you'll be able to control the magnetic field. So you'll have a known value for magnetic field. Q is a known constant if it's an ion or something like that. And the radius of curvature is measured. But the velocity of the particle, how fast it's going as it spins around, is really hard to measure. So let's see how we can measure that. How do you find the velocity of a particle? Well, you can first shoot it through an electric field and a magnetic field at the same time. So if you've got a particle going through an electric field and a magnetic field at the same time, it has two forces on it. So you can make it so that, for example, the magnetic field is this, or magnetic force is this way, and the electric force is this way. And the particle, it'll be going, say, straight through that way. And the only way that it can travel in a straight line, so maybe you put it through a little hole right here, and maybe over here you have a little hole as well. The only way that this charge, electron, can travel through this hole straight through and out this hole, which means if it goes through both holes, it means it's traveling in a straight line, is if these two forces were equal to each other. And so you set those two forces equal, and you can see that the velocity is equal to the ratio of the E divided by the B field. So you can have these two magnetic and electric fields, and you can turn knobs until the stream of particles goes straight through undeflected, not bent left or right. And when you have that, you see what the setting of the E field was and what the setting of the B field was, and then you can calculate what the velocity of those particles must have been. And it does not depend on the charge, so the velocity only depends on the E and B fields. So if you plug this in for the velocity into, let me go back a slide, if you plug it into this formula right here for V, you get that the mass is QB squared R over E. So first you run it through an electric and a magnetic field, and then you run it into just a magnetic field only, it'll start to curve around. You can measure the radius of curvature, and if you know the charge and the magnetic and electric fields, then you can find out the mass of these particles, which helps you then identify what type of atom it is, if it's an unknown atom, or even more importantly, it helps you separate different isotopes. So you can see that the mass depends on, the different radius. If you have a different radius, you'll have a different mass, and likewise, if you have a different mass, you'll have a different radius. So when you shoot particles through, let me get a blank slide here. What you do is you have E and B. So you shoot these particles through E and B. They come out in a straight line, and then up here you have B only. And so they're going to curl around, and this will be a half circle, perfect half circle, and then they'll hit. So you typically have detectors over here. So sometimes they might curl around like that, or they might curl around like that, or they might curl around like that. And these different radius, so this, radius 1, or maybe this one has, radius 2. Anyways, these different radiuses of these circles have to do with the different mass of the particle. So the bigger the radius, the bigger the mass. And if you have different isotopes of the same atom coming through, since different isotopes have different masses, they'll have different radius and they'll hit at different places. And then you can fine-tune this to collect or separate different isotopes. And instead of having them impact right here, you can have another little slot, and they can come out. And then you'll have a beam right here of pure certain isotope that you wanted. So it allows you to selectively pick out different masses out of a sample. Okay, so let's summarize this chapter, not too much in it. Most important couple of things are that electric and magnetic fields self-propagate through space by inducing each other back and forth, and what they create is called an electromagnetic wave, which is really just light and travels at the speed of light, which is 3 times 10 to the 8th meters per second in vacuum. And then second thing is we can use these electric and magnetic fields. Typically, I didn't say this before, but typically when we're using the electric and magnetic fields to test in experimental settings, we want to use uniform fields. So that's where solenoids come into play to create uniform magnetic fields, and parallel plate capacitors come into play to create uniform electric fields. So we can use these to bend the path of the charges, and then we can use it in experiments to find out masses or charges or different isotopes like that. So electric and magnetic fields are really, really helpful for both studying and learning more about the structure of matter in experiments, but also for transmitting information like electromagnetic waves. This is how, cell phones work. Pretty much all the data that's transferred via satellite or anything like that is electromagnetic waves. So we use this on a regular basis as light, but also as a way to transfer information. So E and B fields, absolutely critical to our daily lives.